Welcome to today's explainer. We're jumping right into how we can actually artificially manipulate gravity to solve some seriously complex real-world problems. We're talking about a technology that literally impacts everything from the food on your dinner table all the way to the bleeding edge of space exploration. But first, imagine you're trying to separate things that just won't pull apart under normal gravity. Think about tiny, microscopic particles suspended perfectly in a liquid. If standard gravity isn't strong enough to pull them down, how on earth are we supposed to force them apart? Well, the answer is the centrifuge. You know the one. It's that lab instrument that uses centrifugal force to achieve density-based separation of fluids, gases, or liquids. Basically, by spinning a container at absolutely mind-boggling speeds, it forces heavier elements to the outside. It separates particles based on their size, shape, density, and even their viscosity. So, here's our agenda for today. We're going to look at the power of spinning, the anatomy of a centrifuge, techniques and machine types, how to spin safely, and finally, its real-world impact. Starting off with Section 1, the power of spinning, from gravity to centrifugal force. So let's look at this timeline, because the history here is actually super fascinating. The evolution of the centrifuge takes us way back to the 18th century. A British military engineer named Benjamin Robbins originally built this rotating arm device just to gauge drag on military items. Crazy, right? But then, moving to the late 19th century, the Prandtl brothers took that same concept and invented the first practical centrifuge for something entirely different, separating milk from cream. And from that dairy farm tech, it evolved into the highly advanced, absolutely indispensable tools we use across global science, medicine, and industrial research today. You might be wondering, why do we even need a machine to do this? Well, simple gravity just doesn't cut it for particles smaller than 5 micrometers. At that microscopic scale, particles don't just settle down. They're constantly bouncing around in what's known as Brownian motion. It's kind of like a chaotic microscopic mosh pit. Because they won't just sediment under normal gravity, we have to introduce a massive centrifugal field to finally overpower that motion and push those heavy elements to the outside. Moving on to Section 2, anatomy of a centrifuge, what makes it spin? So looking under the hood, at the heart of the centrifuge is a super powerful motor that converts electrical energy into mechanical energy. This motor spins the rotor assembly, which holds your containers. And these containers, they could be anything from tiny test tubes and cuvettes to literal blood bags. The whole shebang is strictly regulated by a control panel where you set your temperature and speed. And absolutely crucial here, it is all safety locked beneath a heavy lid and latch system to prevent any operation unless it's completely securely closed. Now, what's really interesting here is the contrast in the rotors. On the left, we've got fixed angle rotors. These hold your tubes at a strict 14 to 40 degree angle. Because of this tilt, particles only have to travel a very short distance to hit the wall and slide down to form a solid cluster, or a pellet at the bottom. On the right, though, we have swinging bucket or horizontal rotors. As the machine accelerates, these buckets swing out until they're completely horizontal. This lets the particles travel a much longer distance straight down to the bottom of the tube, which makes separating the liquid on top, the supernatant, from the solid pellet a whole lot easier. Section 3. Techniques and machine types, how and what we spin. At a high level, the scientific community essentially splits centrifugation into 2 main techniques. Over on the left, preparatory centrifugation is all about isolation and purification. This is your go-to when you want to extract specific biochemical components. Think cells, membrane vesicles, or viruses. On the right, we have analytical centrifugation. Here, you're not trying to isolate a product. Instead, you're strictly collecting information to characterize those already purified biomolecules in real time. You're measuring things like their molecular weight, their purity, or even detecting changes in a protein's structure as it spins. Now, if you look at this table, the sheer power of these machines scales dramatically based on what you're actually trying to separate. Your everyday low-speed lab machines run at a max of about 4 to 5,000 RPM. Hematocrit centrifuges, which are used for blood analysis, bump that up to around 15,000 RPM. But check out that bottom row. Highly sophisticated ultracentrifuges can reach a staggering 150,000 revolutions per minute. That is an insane amount of speed, all just to separate out the absolute tiniest of molecules. But it's not just about raw speed. There are highly specialized machines engineered for pretty much every conceivable need. You've got refrigerated centrifuges that hold freezing temperatures between -20 and -40 degrees Celsius, which, is absolutely vital when handling delicate biologicals like DNA, RNA, or antibodies.
Then there are compact microcentrifuges for those tiny 2 milliliter samples. You've got continuous flow centrifuges that process massive quantities without you having to stop and reload the machine over and over. And get this, there are even gas centrifuges designed specifically to separate gas molecules based on their mass, which is critical for separating uranium isotopes.
All right, Section 4. How to spin safely, harnessing massive forces. Because we're dealing with equipment spinning it up to 150,000 RPM, operating this stuff requires a profound amount of respect. Pre-spin prep is absolutely critical. First off, you always have to inspect your tubes for the tiniest cracks or blemishes and toss out anything damaged. But here's the real kicker. You must balance your tubes symmetrically by their exact mass using a scale. Never ever balance just by eyeballing the liquid volume. An unbalanced load at these extreme speeds can cause violent shaking and literally result in catastrophic mechanical failure. So everything has to be perfectly balanced, totally dry on the outside, and tightly sealed. And once that spin starts, your safety protocols definitely aren't over. You lock the lid, configure your settings, but you absolutely do not walk away. You've got to stand there and monitor the machine as it ramps up to its maximum speed. You're listening for any odd noises or violent vibrations that might hint at a balance issue. When the cycle is finally over, you've got to be patient. Wait for the rotation to completely stop before even thinking about touching that lid. And actually, it's best practice to wait an extra 10 minutes before opening it, just to allow any potentially hazardous aerosols generated during the spin to fully settle safely inside the chamber.
Finally, Section 5. Real-world impact, from micro to macro.
Let's zoom out a bit. You probably actually use a basic centrifuge right in your own kitchen. A simple salad spinner removes water from washed lettuce using, you guessed it, centrifugal force. But if you scale that up to an industrial level, giant versions of these machines are doing some serious heavy lifting for society. They're turning dairy to separate out cream and fat. They're working tirelessly in municipal water treatment plants, spinning mud and sludge right out of our drinking water. And out on the ocean, massive centrifuges are separating solid matter from freshly drilled petroleum on oil rigs.
And on the more extreme, highly technical ends of the spectrum, these devices are utterly essential. Clinical labs rely on them to test sedimentation rates of microscopic blood cells, and the pharmaceutical industry uses them to mass-produce bulk biological drugs. On an atomic level, like we mentioned earlier, they're used to extract and separate uranium isotopes for nuclear programs. And on a massive human scale, well, giant spinning rooms literally act as centrifuges to simulate high G-force environments. That's exactly how we train our aeronautic pilots and astronauts to handle the intense rigors of space travel.
Of course, while centrifuges give us incredibly fast, enclosed, and easily automated separation, we do have to acknowledge the trade-offs. Generating that much rotational force demands massive energy consumption. Plus, it produces unavoidable noise pollution and vibrations. And since these are highly sophisticated devices, when they malfunction, they require expensive specialist maintenance. This means labs almost always have to shell out for backup machines. And finally, they inherently struggle to separate exceedingly light particles that have almost negligible mass.
Yet, despite those limitations, the centrifuge remains a foundational pillar of modern science and industry. So having seen how a simple spinning motion can do everything from purifying the water you drink to preparing astronauts for the violent forces of spaceflight, we're left with a pretty exciting question. As we continue to master the artificial manipulation of gravity, what impossible separations will we conquer next? Thanks for joining me for this explainer, and I hope you walk away seeing the invisible forces around you in a completely new light.